Before we understand Java memory model, we need to understand two concepts. The first concept is called out-of-order execution. When you write a program, it's generally a series of statements. You expect that those series of statements will be run in the same order that you have written it. But it is completely possible that the compiler or the JVM or the CPU will change the order of your instructions to drive some performance out of it. And this is done in a way that the program semantics remains the same. So the program output will always remain the same even though these changes are made by the compiler or the JVM or the CPU. Here we have a very small snippet of code, a equal to 3, b equal to 2, and a is incremented by 1. If you convert it, it might look something like this. It will say load a from main memory, set it to 3, store it back. Load b, set it to 2, store it back, and so on and so forth. But if you observe closely, we are loading a twice. And that is why one performance improvement could be you could move that statement of incrementing the value of 1 before you're setting the value of b. In that case, internally, the instructions might look like this. So here you're saying load a, set it to 3, increment it by 1, and store it back into the main memory. And then you load b and do operations on b. And these are the changes that can be done by the compiler or the JVM or the CPU to get more performance like this. The second topic that we need to understand is called field visibility. And this is generally applicable only in terms of multi-threaded applications, which we also call concurrency or concurrent programming. Before we take a look at an example, let's revisit the memory model. If you have a quad-core machine, which of course means you have 4 cores, core 1, 2, 3, and 4, each core generally have a set of registers. Registers are nothing but a memory area which is very small, but it is within the core, and that is why it is fastest to retrieve any value out of it or store value in it. Then one layer farther you have L1 cache, which is again only a memory area set aside for each of the cores. You have L2 cache, which could be shared between 2 cores, and then you have L3 cache and RAM, which could be shared across 4 cores. So in this case, the farther the memory from the core, of course it will induce more latency, but it will have more size and it will be cheaper. With this in mind, let's take an example. Let's say we have a class called field visibility. Here we are setting the value of x as 0. We have a method called writerThread. We are setting the value of x to 1. And we have readerThread method where we take that value x and we set it to some variable called r2. Let's say we create an instance of this and we use the same instance to run 2 threads, a writer thread and a reader thread. Let's say the writer thread only calls this method writer thread and the reader thread only calls this method of reader thread. Let's say both of these threads run parallelly. So as shown here, let's say writer thread runs on core 1 and reader thread runs on core 2. Here, initially the value will be stored in the shared cache, which could be the RAM, and that value is 0. When the writer thread method is run, that value will be incremented to 1. But that increment will happen only in its local cache. It is completely possible that x equal to 1 is never pushed into the shared cache. In shared cache, the value of x is still 0. And that is why when the reader thread runs on core 2 and when it says get me the value of x so that I can assign it to r2, it is completely possible that we get the old value of x, which is 0, and we assign it to r2. And that is why the r2 value will be 0, which is wrong because x should have been 1 here also. And this is called field visibility issue because the variable x is not visible in its true sense to the reader thread. Java provided a solution for that. It says that you use a keyword called volatile. If that keyword is volatile, JVM will ensure that when the x value changes to 1, it is flushed or pushed into the shared cache so that when any other core tries to load that value, it will always get the updated value. So making this one small change of making the type of the variable is volatile ensures that the field visibility problem is solved. Now that we understand those two concepts, understanding Java memory model is very easy. Java memory model is nothing but a specification or a set of rules which guarantees the visibility of variables or visibility of fields when you have reordering of instructions. So we saw both the concepts. We saw reordering of instructions to increase the performance, and we saw there could be problem of visibility of the fields. Java memory model enforces that all the JVM have to implement these set of rules so that if you run a program on one JVM, if you pick that program, run on another JVM, your program runs exactly the same. Okay, so Java memory model rules have to be implemented by all the JVMs. There's one more concept here, and that concept is called happens before relationship. Let's say we have the same example. Before we have x, the value of x is being written as 1, and here in the reader thread method we are reading the value of x and putting it into R2. Let's say we have three other variables which are not volatile, they're simple regular variables, and we are setting their values a, b, and c as 1. And here, after reading the value of x, we are reading this value of variables a, b, and c. Java memory model ensures, or there is a rule, that any fields that are written to before you write x, those values should be updated and visible to any other thread after it has read the value of x, right? So it says whatever has happened before this, it should be visible after this, and that is why it is called a happens before relationship. In fact, this is not just applicable to volatile. This concept of happens before relationship and field visibility is also applicable to things like synchronized keyword, synchronized method, synchronized blocks, locks, lock operations, some operations of the concurrent collections, and some thread operations like join and start. Java memory model also has some special behavior about final fields, but let's not talk about that. Here we have the same example as before, but instead of having x as volatile, I made a mistake and wrote it volatile, but let's say this is not a volatile. We could still have the same result by using a synchronized keyword. So if we synchronize this operation to write, and when we synchronize this operation to read from x, there is also a rule in Java memory model that it should have the updated value of x, and it also has the rule of happens before relationship. So all the values which were updated before synchronized have to be updated and visible after the reading of synchronized. Yeah, and there is a small caveat here that the synchronized keyword should be applied on the same object. So here we are doing synchronized on this, the instance of this class of synchronized field visibility. If we use the synchronized keyword on different objects for writing and different object for reading, it will not work. Of course, it's much more clearer if you, instead of relying on happens before relationship, you put everything within the synchronized block. So here we have the same thing, but we update all the variables into a synchronized block, and we read all the variables by synchronizing on the same object of this. Again, there was no need to have a volatile here, it's a mistake of the code. Similarly, we can do this using lock operations. So we can use a lock to perform the lock operation, update the variables, perform the unlock operation. And in the reader thread, we can again do the lock operation and perform the operations and do the unlock operation. And Java memory model ensures or guarantees that all the values updated here will be updated and available to the reader thread here. With this, now we understand what is a Java memory model. And using this, typically there is also an interview question. So take a look at the code on the left. So we have similar to what we did with x equal to 1, writing to it and reading from it. We have a boolean flag. It is not a volatile, it's a simple flag. Here the writer thread is setting it to false, and there is a reader thread and it's performing some operations in a seemingly infinite loop. So it says while flag, and the flag's initial value is true. So it says while true, keep doing these operations. And after some time, maybe in the writer thread, you change the value of flag to false. And with Java memory model, if it's not a volatile, it's completely okay for a thread to never flush the updated value of flag into the shared cache. And that is why it is completely possible that the reader thread will never stop. It will go into an infinite loop and keep working. And to fix this, we can use the memory model rule and we can introduce this keyword of volatile. Once we have it as volatile, then any operations of write on the flag have to be flushed into the shared cache and have to be picked up by the reader thread, and that is when this reader thread operations will stop. And that's it. That's all there is to Java memory model. Thank you. Bye.